Okay, so for our data science project, we wanted to analyze the correlation between posts on Twitter about a certain stock and that stock's performance over a given day. So the first thing we did was import the necessary libraries and modules, and then we started our data analysis by installing the Polygon API client, which we use to analyze stocks, to our virtual environment. And so once that is installed, we can then import the Polygon client. We set our API key to a variable and then use that variable to authorize our Polygon client. For collecting the data, we made a list of tickers corresponding to companies we wanted to analyze, set some parameters for the search, and then we performed a search for each stock and appended the results to a list. For each of those result items in the list, we created a data frame with the date, performance, which is the stock's closing price minus the opening price, and the range, which is the highest price minus the lowest price during a given day. Um, and then we created new weighted performance and weighted range variables, which was the normalized performance and range. We created a new activity metric, which was where we took the weighted performance, added it to the weighted range, and then normalized that. Um, and we made new data frames with the date and the activity metric um, for each day analyzed of each stock and appended those data frames to a new list. Um, Next, we needed to analyze the Twitter data, so we started by importing the Tweepy library, um, setting Twitter API keys to variables, including the bearer token, consumer key and secret, and the access token key and secret. Um, Next, we authorized the access to the API, and then we authorized the Tweepy client to perform the searches. When we were collecting data from the Twitter API, we created a list of Twitter usernames corresponding to the company CEOs for the stocks we analyzed. We then set parameters for the search, and we used each user ID of the usernames to collect their tweets in a certain time range, um, from which we got the date, if they tweeted on that date, and the number of likes, retweets, and quote tweets that their tweet got. And we created data frames with all of that data for each Twitter username and appended it to a list. All right, so once that's done, we needed to join the stock and the tweet data. So to do this, we merged the data frames from each corresponding stock and Twitter username to create new data frames, including um, the date, the activity metric, um, as well as if there was a tweet on that day and the number of likes, retweets, and quote tweets that tweet got. And if there were zero tweets, then all of the numbers were zero. Um, we then concatenated all of those data frames into one big data frame um, to give us the data we would be using to train and test our models.
So the first model we selected was a random forest regressor, and what we started with was splitting our data into input and output, and then splitting that into train and test sets. From there, we built the model and then fit it to the training data, and then after that, we generated a list of predictions for our testing set, which I listed right here. After that, we calculated the mean squared error, which is pretty low, the value of 0.02. From there, we started to tune the hyperparameters, and the hyperparameter we tuned was the number of estimators, which is the number of trees in the forest. So we tested between 85 and 115 trees, and then generated a graph to show the mean squared error values for each number of estimators. And then we found that the most accurate number of estimators is 102, so 102 trees, and that generated a mean squared error of 0.02. The next model we used was a support vector machine. In phase 3 of our report, we said we were going to use logistic regression, but that is a classification algorithm, and we're predicting a numeric output, so we had to change that to a support vector machine. So similar to the the random forest regressor, we split our data into input and output, and then split it into trained test sets. And from there, we normalized all of our input features, and then built the support vector machine from that. And once again, we scaled the test data to match the training data and generated a list of outputs, which are listed right here. The mean squared error that we generated was 0.019, which is better than the random forest regressor. And the hyperparameters we tuned are listed here in this params column. We tuned the C value, kernel value, and the degree. And we found that the best parameters for that were, for C, it was a value of 1, for degree, a value of 1, and for kernel, poly. And that generated a mean squared error of 0.017. Then our last model is linear regression. We, once again, split it into input-output, and then split that into train test. We fit the model to that training data and then generated a list of outputs, same as before. And then we calculated the mean squared error, which was 0.02. And we did not tune any hyperparameters here because our output data was already normalized, so there was nothing left to tune for this model.